The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to this webinar presented by Digital Systems KTN and the 451 group. We have John Barr with us, a distinguished analyst who is going to talk about cloud, the HPC, and the Multicore. Right now, there are only 5 attendees. We will wait a couple of minutes to allow other people to join. So we'll be back with you in another 2 minutes. Okay, we will start. Welcome everyone to this webinar. Today we have John Barr, Research Director for Financial Markets and Head of EU Research from the 451 group with us. John is responsible for companies' research activities within the European Commission framework. His main focus area is high-performance computing as applicable to financial markets. John has around 30 years of experience in the IT industry. He has been involved in writing compilers and developing tools for the HPC platforms. He has spent a significant time of his 30-year experience at various technical roles with many HPC vendors. He has trained people, written compilers, ran benchmark tests, and he has supported customers in the pre- and post-sales roles. Today he'll be talking about the cloud, the HPC, and the multicore, and its potential impact on the industry. We are delivering this webinar using a third-party vendor called gotomeetings.com. All the participants will be on mute. If you have any questions, you can type them using the questions tab. If you need any help, please use the raise hands feature, or you can chat with me. So over to John now. Thank you.
Thanks for that introduction, Mahesh. Yes, I cover both high-performance computing and the use of technology in financial markets in my research nowadays. So my HPC involvement is across all markets and not just limited to the financial markets. The 451 Group, for those of you that don't know, is an independent technology industry analyst company focused on the business of enterprise IT innovation. And we have two subsidiaries. Tier 1 Research covers the business of data centers, and the Uptime Institute brings insight to infrastructure issues. That's the buildings, power and cooling for data centers. Our published research in HPC covers technology, vendors, applications and users, and we publish long reports such as these, which are sort of 40 or 50 page long, and many short reports covering vendors, technology, products, competitive analysis, trends, standards, and also users. I'll start with an HPC backgrounder for those not familiar with this space. Then I'll look at current and emerging issues that affect HPC users today, providing real-life examples of how these affect application performance. So what is HPC? Well, high-performance computing is often called numerically intensive computing or number crunching. Computer simulation today is the third branch of science, together with the traditional theory and experiments. Now, a typical data center may see something like 10% utilization for their servers. If they've done a really good job with virtualization and consolidation, maybe 60% utilization. But a typical HPC facility that is running at less than 90% utilization will feel that they're not doing their job properly. So HPC systems tend to, run right up to the red line all the time, doing intense floating point calculations. Early supercomputers used a vector architecture, that is, they were built to process vectors or arrays of data efficiently. The leading vector systems were built by Cray starting in the mid-1980s, and CDC, Fujitsu, NEC, and Hitachi also produced vector systems. A top-of-the-range system then would have cost you of the order of $30 million. In the 1990s, many alternative architectures were tried in order to deliver high performance at lower cost. Convex built vector machines from less exotic technology than Cray, delivering perhaps a quarter of the power of a Cray, but at a tenth of the price. Attached array processors from floating point systems and others augmented the number crunching capability of mainstream mini-computers. And massively parallel systems were built from a large number of low-cost components, with a connection machine from thinking machines and systems based on the InMOS transputer being popular for a few years. But with many different complex architectures, there was a real shortage of software. Application developers could not afford to port and tune their large codes to a new machine if they could only expect to sell 10 or maybe 20 copies. In the last decade, the supercomputer architecture of choice that has emerged is basically a network of commodity servers. It's taken time for this model to be accepted because applications started life as serial codes, then they were optimized for vector machines, then shared memory multiprocessor machines where a single code could run on multiple processors simultaneously that were able to share a common pool of data. For applications to run on a network of servers, the programming model is very different, and it took many years for a significant number of applications to be rewritten and for a generation of computer scientists to be retrained. And I'll talk about programming models in a bit more detail later on. An x86-based cluster may use Intel or AMD processors with any number of cores per processor from 1 to 12 currently, and either an Ethernet or InfiniBand interconnect. Many different configurations can all run most shrink-wrapped cluster-ready applications straight out the box. which has led to a great growth in HPC, because one application can be delivered and run on platforms from many different vendors. The fastest supercomputer in the world today is a Cray XT5 system called Jaguar at the Oak Ridge National Labs in the States. It's based on standard dual-socket servers with 6-core AMD Opteron processors. And as you can see from the numbers, it's got 18,000 compute nodes, almost 250,000 cores, and 300 terabytes of memory. I guess in the next top 500 list that I'll talk about later on, that will be published next week, there's a Chinese system which is going to eclipse Jaguar. But for now, Jaguar is top of the tree. Now, multicore is one of the areas I want to cover today, and this is a multi-dimensional problem. It's not just 2, 4, or 6 cores that we need to consider. Within a year or two, we'll have 50+ cores in a processor. And when you have a small number of cores, that can be treated as just more processors in a shared memory system. You just allocate more threads, jobs, or virtual machines. But a large number of cores almost guarantees that you're going to have some sort of resource conflicts, and we need to find ways of avoiding these. And how do you write efficient parallel code for an x86 platform when you don't know how many cores will be used, what the cache architecture looks like, how the cores are interconnected, how many multiple processors make up a single system, and then how the overall systems are connected together? And as more and more people write parallel codes, and now it's not just HPC experts, how do you trap concurrency bugs before they trap you? Parallel compilers have not made significant advances in the last 2 decades. So multicore brings great benefits, but there are some significant software issues that we need to deal with. Developers have to optimize applications to get the best performance from multicore, but they have to go a step further and target application accelerators such as GPUs to get the very best performance in some areas. This provides a similar compute model to that used by the FPS array processor in the 1980s, but now the accelerator is the size of a paperback book instead of the size of a fridge, and much more powerful. Systems are scaling in many dimensions: the number of cores in a processor, the number of systems in a cluster, and the size of grids. Intel has produced 3 development platforms with 32, 48, and 80 cores, so it won't be long before a dual-socket pizza box server has over 100 cores. Software tools like that from ScaleMP can enable multiple systems to behave as a single system. And just do the maths. If you've got 100 systems with 100 cores each, that's 10,000 cores in a single system. If technology continues to advance at the same pace, a single cabinet will hold 100,000 cores by the end of the decade, by which time the first Exascale system will be in operation. That's 500 times more powerful than Jaguar's 224,000 core system. Grid computing was a technical precursor to cloud computing and has been used by many academic researchers for over a decade to share compute, scientific resources, and to build virtual organizations. At one end of the scale, a department may have a single rack cluster. At the other end of the scale, you may have a worldwide resource comprising thousands of systems, like the grid used to process the Large Hadron Collider data at CERN. And in between, resources can be used effectively across an enterprise. The commercial realization of the utility computing capability promised by grid is cloud. Its flexibility has seen cloud adoption experience phenomenal growth. But although the genesis of cloud is grid, most clouds are actually not very good at running HPC applications. There's a conflict between optimization and virtualization. Some trivial parallel applications can run on